You know, when you're talking to an LLM, it can feel, well, like magic, right? It's just so good. But here's the thing about a good magic trick. There's always a secret. So today, we're going to pull back the curtain and find out exactly how these models learn to talk.
See, the trick isn't some single lightning bolt invention. Nope. It's more like a 40-year chain of innovation, with brilliant researchers standing on each other's shoulders, adding one crucial link at a time. So let's trace that chain. Let's see how the magic is really made.
All right, so where do we even start? Well, the very first hurdle was, language itself. Early researchers had this idea to use statistics to predict the next word in a sentence, but they ran headfirst into a wall. A problem so big, so fundamental, it earned itself a pretty epic name.
And that problem is the curse of dimensionality. And yeah, it sounds super intimidating because, frankly, for a long time, it was a total deal breaker. Just think about it for a second. How many ways can you arrange 10 words? Now, try to imagine doing that with 1,000,000. The sheer number of possible combinations just makes any kind of traditional statistical approach fall apart.
I mean, with a vocabulary of millions of words, trying to calculate the odds of every possible sentence is like trying to count every single grain of sand on a beach. It's just not going to happen. Your training data, no matter how massive, will never come close to seeing all the combinations. So those early models, they just couldn't generalize. They were stuck.
So the first real crack in this seemingly impossible problem was this beautiful, elegant idea. What if, instead of treating words as just, letters on a page, what if we could represent a word's meaning mathematically? This was a total game changer. For the first time, computers could start to understand the relationship between words. So what if words to become vectors? Now, this idea of distributed representations had actually been floating around since the 80s, but it was Yoshua Bengio in 2003 who really connected the dots and applied it to language. He suggested learning a unique vector, an embedding, for every single word. But the real breakthrough came in 2013 with Tomas Mikolov's word-to-vec, which finally made the whole approach efficient enough to work at a massive scale. And that unlocked everything. And this is the incredible result. By turning words into these numerical vectors, the models started to learn the relationships between them. You could literally do math with meaning. Take the vector for king, subtract the vector for man, add the vector for woman, and you get a vector that's incredibly close to the one for queen. This isn't just a party trick, it's the computer capturing real-world concepts. A huge leap forward. Okay, so that's a huge step. We understand words now. But language isn't just a jumble of words in a bag, right? It's all about sequence, and order, and context. A word's meaning can totally flip depending on the sentence it's in. And that was the next big mountain to climb. The first attempt at a solution came with what are called sequence-to-sequence models. These could finally handle whole sentences. But in a classic case of solving one problem only to create another, they introduced a brand new issue, the context bottleneck. Models like recurrent neural networks, or RNNs, works by reading a sentence one word at a time. But here's the catch. To understand what it just read, it had to cram the entire meaning of that sentence into one single, fixed-size vector. Think of it like trying to pack for a month-long trip using only a tiny handbag. For longer sentences, a ton of nuance and important information just got lost. It was a serious bottleneck. To get past this bottleneck, researchers came up with what is, and I'm not exaggerating here, probably the single most important concept in all of modern AI. They taught the models how to do something we do all the time. They taught them how to pay attention. The big idea behind attention is actually pretty simple. Instead of forcing the model to cram everything into one memory vector, what if you let it look back at the entire input sentence, at every single step of the process? It could then decide for itself which words are the most relevant for what it's doing right now and give them more weight or more attention. Let's make that a little more concrete. Think about the sentence, "The robot picked up the ball because it was heavy." The model needs to figure out what it is referring to. The query is basically the model asking, hey, what is it? The keys are all the possible answers it can look at, robot and ball. So the model compares its query to those keys and figures out that heavy is way more related to ball than to robot. So it retrieves the value, the actual meaning of the word ball. This dynamic search process completely shattered the context bottleneck. Attention was so powerful, so effective, that in 2017, a landmark paper from Google Brain came out with a title that was also a really radical question. What if we just got rid of everything else? What if, really, attention is all you need? You see, the big problem with those old RNN models was that they were sequential. You had to process the first word before you could process the second, and so on. It was painfully slow. This new transformer architecture just threw all of that out the window. By relying only on attention, it could look at all the words in a sentence at the exact same time. It was massively parallelizable. This new architecture used something called self-attention to figure out how all the words in a single sentence relate to each other. And it added this really clever trick called positional encodings, which are basically like little GPS coordinates stamped onto each word so the model knows the original order. This combo of parallel processing and deep contextual understanding, well, that was the final piece of the puzzle.
The transformer didn't just solve a technical problem. Its parallel design unlocked a completely new philosophy for building AI. Bigger is better. It allowed models to be trained at a size and scale that was just unimaginable before. And that brings us to the modern era, the era of scale.
But with massive scale, you get new challenges. A model that's just trained to predict the next word isn't always helpful, or even safe. So researchers developed a process called reinforcement learning from human feedback, or RLHF. It's basically a three-step dance. First, humans rank different model responses. Second, a separate reward model is trained to predict what the humans will like. And finally, the main LLM is fine-tuned using that reward model as its guide, aligning it with our values.
And with that foundation in place, the race to scale was on. Just look at this chart. In 2018, GPT-1 had 117 million parameters. Pretty big. By 2020, GPT-3 had 175 billion. 2 years after that, Google's Palm model hit 540 billion. The growth is just absolutely exponential.
And here's where things get really fascinating. With all this scale comes complete surprises. These emergent abilities, like chain-of-thought reasoning, they just don't exist in smaller models. They only start to pop into existence once the models cross a massive threshold, somewhere around the 100 billion parameter mark. So size isn't just about getting more of the same thing. It creates something qualitatively new.
This all points to something AI pioneer Richard Sutton calls the bitter lesson. And the lesson is this: simple, general methods that can just leverage massive amounts of computation almost always win out over more complex, handcrafted human-designed systems. And it's bitter because it kind of suggests that brute force scale is often more powerful than our own cleverness.
And that brings us right back to where we started, the magic. From the curse of dimensionality to word vectors, through the context bottleneck to attention, and finally unlocked by the transformer and the era of scale. It was never just one trick. It was a whole chain of brilliant ideas. And that leaves us with one pretty profound question. If we're already seeing abilities emerge that we never explicitly programmed, what happens when we scale even further? What magic trick will these models learn to do next?